Now we are going to discuss about basic timing circuit. This is explaining the basic timing circuit, and those are the waveforms of basic timing circuit. First, I am going to explain the operation of basic timing circuit. The basic timing circuit consists of comparator as well as SR flip-flop. We may also call it as RS flip-flop also. We all know that SR flip-flop functional table. When S is equal to 0, R is equal to 0, we may get output as previous state. S is 0, R is equal to 1, we may get the output as 0. And S is equal to 1, R is equal to 0, we may get the output as 1. And if both are ones, then it is the undefined state. So we all know the functional table of SR flip-flop. If we know the operations of comparator and SR flip-flop, then with the help of remaining elements, those are resistors, capacitors and transistors, we can easily construct the basic timing circuit. Now, to understand the operation of this circuit, first I am going to assume my output Q bar is low. Q bar is output, not Q. So the total timing circuit operation, the output is Q bar. Okay, if my output Q bar is low, then my output Q will becomes the output Q will becomes 1. Why? Because Q bar is complementary for Q. If Q is 1, then Q bar is equal to 0. So if my Q is equal to 1, then it activates or it drives the transistor Q1 into saturation. Why? Because here it is Q1 emitter is connected to ground. That's why it is discharges. And there will be no voltage across the capacitor C. Okay, so there will be no voltage across the capacitor C. The other end of the capacitor is connected to ground. No, so the capacitor is shorted. Now coming to the comparator. Comparator consists of two inputs. One is the reference input and the other one is the input which we are going to be apply. Okay, here in this case the inverting input terminal is nothing but the reference voltage that we are going to be considered as control voltage, and the non-inverting input will be taken as threshold voltage which we are applying to the input of the comparator. Now this control voltage is generated with the help of potentiometric divider. The potentiometric divider is generated with the help of R1 and R2. So with the help of this potentiometric divider, we can easily calculate the control voltage. How can we calculate? So if you want to calculate the voltage at this position, so control voltage is equal to VC into R2 divided by R1 plus R2. And we all know that VCC is nothing but VC, that we are going to consider it as 15, and R2 will be taken as 10, and R1 plus R2 will be taken as 5 plus 10, which is nothing but 15. Okay, 150 by 15. So we will get it as 10 volts. So we are applying the control voltage with the help of potentiometric divider. Those resistance values are 5 kilo ohms and 10 kilo ohms, and supply voltage VCC is plus or minus 15 volts. With that, we set the reference voltage, which is nothing but the control voltage. In this case, that will be set to 10 volts. Now we are going to see the threshold voltage, and this non-inverting input of the comparator is considered as threshold voltage that will be applied because of the charging and the discharging of the capacitor. Okay, if the capacitor is charging, then that will be applied with the threshold voltage to the non-inverting input. If the capacitor is discharging also, we will apply that voltage to the non-inverting input at the threshold voltage. And after comparison of these two voltages, we may get the output as high or we may get the output as low. Okay, now initially we are assuming, to understand the operation, we are assuming Q is equal to 1. What happened if Q is equal to 1? When Q is equal to 1, it drives the base of transistor Q1 into the saturation. Then what happened? The capacitor is discharges, okay, and the other end of the capacitor is connected to ground, so the capacitor is shorted. The voltage across the capacitor in this case is 0 volts. Okay, now we are applying the voltage at the threshold input of the comparator, and it will be comparing with this control voltage. And when it is comparing with the control voltage, obviously the control voltage value will be very high. Why? Because this is 10 volts and this is 0, so we will get the negative value. Negative means we are considering comparator output is minus Vsat. Negative means we are considering 0, so we will be applied S is equal to 0. Once S is equal to 0, obviously what happened for the Q? Q will be equal to 0. When Q is equal to 0, it cut off the transistor. Okay, then the capacitor will be charging through the resistance R easily. Okay, now the capacitor voltage VC will be applied to the non-inverting input of the comparator. Now we are going to compare these two voltages. If the threshold voltage value is not greater than the control voltage, then the output will not be changed. Once the threshold voltage is greater than this control voltage, immediately the comparator output goes to plus Vsat. Here plus Vsat means we are considering it as 1, whereas minus Vsat means we are considering that as 0. So plus Vsat, then immediately S is equal to 1. What happened if S is equal to 1? Immediately Q will be equal to 1, and which drives the Q1 into saturation. Okay, then immediately the capacitor is discharges. So the capacitor charging and discharging is depends upon the output of SR flip-flop or RS flip-flop, and the timing of charging as well as the discharging of the capacitor is depends upon the elements which we are using. Here is R and C. Depending upon the values of R and C, the time duration of the charging as well as the discharging is depends. Now here I am explaining the waveforms of basic timing circuit. From this circuit operation, I explained the waveform. Listen clearly, it is easy to represent the waveforms once we can easily understand the operation. That is, if Q is equal to 0, what happened? If Q is equal to 0, Q1 is off. Okay, when Q1 is off, what happened? The capacitor is charging through R. So when Q1 is off, what happened is the capacitor is charging. Okay, when Q is 0, obviously what happened for Q bar? Q bar is equal to 1. And listen, the capacitor charging is always exponential. That's why here we are representing it as exponential. And whenever the capacitor is charging, then we will get the output as a pulse width duration, and T on pulse width will be generated, and that pulse width duration is depends upon R and C. If you observe this, Q1 is on. If Q1 is on means Q is equal to 1. Then Q bar is equal to 0. Q is equal to 1 means Q bar 0. That's why I am representing the output voltage as 0. That means Q is on. Output is Q bar. Listen carefully, not Q bar. That's why it is 0. Once Q1 is on, Q1 is on means Q is equal to 1. Okay, Q1 is on, at the time the output is 0. When Q1 is off, Q1 is off means Q is equal to 0, Q bar is high. That's why here the pulse width is high. And the pulse width time is depends upon the charging of the capacitor. That's why while the charging of the capacitor is generated when Q1 is off. Once Q1 is off, then the charging of the capacitor will takes place. At that time we get the pulse width at the output, and the pulse width time is depends upon the elements R and C. This is about the basic timing circuit, and this basic timing circuit will be used in the IC 555 timer. For the construction of IC 555 timer, we are going to be used this basic timing circuit operation. Now we are going to discuss about block diagram of IC 555. Here I am representing the pin diagram of IC 555. While I am explaining the pin diagram, I may also explain the block diagram of IC 555. Here it is an 8-pin IC, which is IC 565. Those 8 pins are: first pin is ground, and the second pin is trigger, third one is output, fourth one is reset, and coming to the fifth one is control voltage, sixth one is threshold, and the seventh one is discharge, and the eighth one is plus VCC. Okay, the main use of IC is, without knowing the internal architecture of the IC, we can easily use the ICs by knowing all these 8 pins. Now I am going to explain each and every pin in detail. First pin is ground pin. Okay, with respect to the ground, we are going to measure all the voltages. Okay, for every IC we require ground pin. Without ground pin we may not see any ICs. Okay, so that is the very important pin for all the ICs, ground pin. Okay, so we are going to measure all the voltages with respect to ground. And coming to the second one is trigger. Okay, while I am going to explain the trigger, I am coming to this IC 555 block diagram. Here we are having 2 comparators. Okay, internal architecture of IC 555 is like this. It consists of 2 comparators. What are they? Comparator 1 is this, and the comparator 2 is this. And the trigger we are going to discuss, and the trigger input is applied at the inverting input of the comparator 2. Okay, with the help of voltage divider, that means with the 3 equal resistor, okay, we can design the non-inverting input of comparator 2 is 1/3 VCC. 3 equivalent resistor voltage divider is used to set this voltage to 1/3 VCC, and this voltage is always compared with respect to the trigger input. Okay, whenever the trigger input is less when compared to the 1/3 VCC, then comparator 2 output will goes high. Once if it goes high, obviously the output of the flip-flop will goes low, and the output of the IC 555 will goes high. Why? Because the main output is Q bar, which is the output of the 555. Okay, and the Q is the output of RS flip-flop. That's why what I am telling is, if the comparator 2 output is high, then the main output of the 555 will be high. Now coming to the next one is third pin is output. Okay, across the third pin we are going to collect the output, and the output is nothing but the complementary output, and we may connect the load at the outputs. There are two ways to connect the load at the output. One is we may collect the load at pin number 3 to ground, and another way is we may collect the load in between pin number 3 and pin number 8. That is another way of connecting the load to at the output. That is about the output. And the fourth one is nothing but the reset pin. Once we connect the reset pin to ground, then it stops the working of the IC 555. That means the reset pin overrides all the operations of IC 555, and it will be used as a on and off controller for IC 555. Okay, once the reset pin is momentarily connected to ground, then it stops working of IC 555. Okay, next coming to the control voltage, and this is the pin that is inverting input of the comparator 1 will be treated as control voltage. Generally in most of the applications we doesn't require any external control voltage, so always the control voltage will be fixed to 2/3 VCC value for IC 555 timer. Okay, whenever you require the external control voltage, then you will apply the external input at this pin by changing the control voltage greater than or less than 2/3 VCC value, which is used for producing the pulse width modulated output signals at the output side. So most of the cases we will not use the external control voltages. IC 555 internally consists of 2/3 VCC voltage, but some of the applications we require external control voltage. At that time you have to apply the external input through this fifth pin, which is nothing but the control voltage. Next, coming to the threshold voltage, the sixth pin, which is nothing but the threshold voltage. Whenever you want to apply the external input to the comparator, okay, you may apply with the help of threshold pin to the comparator 1. At 2 we are applying at the non-inverting input. Whenever you require external inputs for the IC 555, you may apply the external inputs through the threshold voltage pin. Okay, that threshold voltage pin is nothing but the non-inverting input of the comparator 1. And now always the threshold voltage is comparing with the control voltage. If the threshold voltage is greater than this control voltage, then what happened? Then the comparator output is plus VSAT. Then plus VSAT is nothing but we will be treated it as 1, and SR flip flop S will be equal to 1, then automatically Q will be 1, and the main output of the IC 555 is equal to 0. Okay, whenever your control voltage is greater than threshold voltage, then what happened? You may get the output as minus VSAT. Minus VSAT is nothing but 0. We will be applied at the S input. We may get the output Q bar as 1. Why? Because Q is equal to 0, then obviously Q bar will be equal to 1. This is about the threshold voltage. Next one is discharge. The discharge pin is connected to QD transistor collector pin. Okay, this QD transistor is also called as discharge transistor in this case. There will be no separate discharge transistors and charged transistors are there. Depending upon this pin connection, we may treat it as a discharge transistor. So once if your Q is high, then what happened? Then QD will goes into the saturation, and if you are connecting any external capacitors across this discharge transistor, that will be charged. When Q is equal to sorry, that will be discharged. When Q is equal to 0, what happened? Then the QD transistor will be off. Then if you are connecting any external resistors and capacitors and that capacitor starts charging, that we have seen it in the basic timing circuit. That is the thing we are explained for the discharge. Last but not the least is plus VCC. What is plus VCC? The supply voltage required for the operation of IC 555 is from plus 4.5 volts to 15 volts. This is the range of supply voltage required to operate this IC 555. Okay, this is about block diagram of IC 555. Here I want to tell you two main things. One is when the flip-flop output is goes high and when the flip-flop output is goes low. I am not telling about the total output. Total output means Q bar. Once you know the value of Q, then you can clearly understand the value of Q bar. Okay, so what is Q? When the output of the flip-flop is high, that is when the threshold voltage is greater than control voltage, which is nothing but 2/3 VCC, then the Q will be equal to high value. Okay, once the Q is high, then automatically Q bar is equal to 0. Okay, whenever the very well known about what happened when threshold is less than 2/3 VCC and trigger is less than 1/3 VCC. Okay, with this background of IC 555, we can easily explain the monostable multivibrator using IC 555 as well as astable multivibrator using IC 555. And that's why what I am telling is IC 555 is a very important device which is used for the timing application. We may use it in the multivibrators also for the generation of the timing applications. Okay, there is a small correction which is nothing but when the trigger is greater than 1/3 VCC, what happened? You may get minus VSAT. What happened when we get minus VSAT? That means you applied 0 here. Once it is 0, whatever may be the value of S, that will be applied at that will be generated at output Q. So what I want to explain is when trigger is less than 1/3 VCC, now what happened? When trigger is less than 1/3 VCC, then the output of the comparator 2 is plus VSAT. When it is plus VSAT, then R will be equal to 1. If R is equal to 1, then obviously S will be equal to 0. S is 0, Q is equal to 0. Okay, 1 Q is equal to 0, then you may get Q bar is equal to 1. Okay, so these are the two main important points you have to remember while you are going to know about IC 555. Listen carefully where I am going to take 1 and 0. For plus VSAT, I am going to consider it as 1. Okay, for plus VSAT we will be consider it as 1 and for minus VSAT we may consider it as 0. Okay.